Hey, so welcome back. What we're going to look at right now is, of course, the enolates that are associated with esters, and then we're going to look at some intramolecular reactions. We'll just go straight ahead and just show you that this is the Kleisen. And with the Kleisen, you should realize by now that we have here 2 moles of an ester. Yeah? 1 mole will act as a nucleophile, i.e. an enolate. We're going to achieve this by using a base. And then the other mole will act as an electrophile. Now, remind yourself that the electrophilic species, i.e. this ester that's going to be the electrophile, is an acyl derivative. And so the reaction with this nucleophile is addition-elimination. The product is a beta ester. So this is your main carbonyl. This is the coupling that occurred. And of course you can see that we have on the beta carbon an ester, the Kleisen. So yeah, if you note, right, we have here the nucleophile, a box standard nucleophile attacking our electrophilic center. We end up with this tetrahedral center, this tetrahedral carbon, this tetrahedral intermediate, where collapse of alkoxide, this lone pair alkoxide, into this carbon recovers your carbonyl and at the same time ejects this leaving group. And so addition, elimination realizes substitution. You can see now the nucleophile that we have in the Kleisen is the enolate of an ester. So of course we can go ahead and add, followed by eliminate. And the product, again, let me iterate, is the beta ester. So we can go ahead and answer this question quite easily. I'll pause it while you go ahead and think through. So if you think carefully, it is not an addition reaction. It is not an addition reaction. So of course we can also eliminate, well, no, we should not do that just yet. That is a bit jumping to conclusion. So let's get rid of that. And then of course it is a substitution. Yeah? Let's have a look at this question here. There is elimination of the ethoxide, but it is not in the step to form the nucleophile. The step to form the nucleophile is of course the deprotonation step to form the enolate. So this is how you form the nucleophile. Yeah, you have the base with an active lone pair, negatively charged of course, because it's a strong base. There's the attack, and then you end up with, yeah, that pair of electrons residing on the carbon. And of course, there is going to generate an enolate that is resonance stabilized. So the correct answer there should be B. Here's a detailed mechanism, and I want you to pause and go ahead and take a shot at this. Firstly, before you go, you should realize by now that we have our base, which we just showed you a while ago, and that will attack the alpha proton of that enolizable carbon to generate the enolate that is resonance stabilized. That enolate will then act as your primary nucleophile attacking the electrophile. Now, the electrophile in this case is going to be the species on the right, which is your unchanged ester. So identify the nucleophilic center identify the electrophilic center, do the attack, see what comes out as your intermediate, and the fate of that intermediate will be terribly important to us, yes? Realizing that that electrophile on the right is a carboxylic acid derivative, yes? So go ahead and do that for us, and I'll meet up with you in a second. You can see immediately that we have here the attack. So this is our nucleophilic center. We'll attack our electrophilic center. And of course, this has to break. And so we end up with this carbon being our tetrahedral center. It is an alkoxide with a very good leaving group. And so once it collapsed to reform our carbonyl, we will eject this species. The net effect is, of course, the formation of the beta ester. Look at it carefully. Beta. Alpha. It's a beta ester. Beta relative to this carbonyl. It is a condensation because we have here an ethoxide plus the proton that we eliminated earlier on, removed earlier on, and that net is ethanol, small molecule. The beta keto ester. Like the aldol condensation, mixed Kleisens are terribly, unattractive. Why? Because as you can see here, we have a pentyl species and a propyl species, and we have two different types of enolizable species, and so we'll end up with 4 different products, and that's really, really gross. Yeah, very hard to separate. So what we can do is we can tailor this reaction. So this is a tailored Kleisen, where one species, the ester that's going to be the electrophilic portion of your reaction, does not have an enolizable carbon. While the other species, in this case, this is going to be your nucleophile, has enolizable carbon. Yeah, and there's the alpha proton that you can deprotonate, and so the coupling will be between these two guys here. So this is the new bond. Note, the ester of the nucleophilic portion of your Kleisen is retained. Can you see that? The ester of the nucleophilic portion, this is the nucleophilic portion, this is the electrophilic portion, so the ester is retained. And so this is, where your alpha carbon was, yes? So with that, we can answer this question quite simply. Why? It says, predict the starting materials and ask you what type of reaction it is. Well, you can see immediately you have an ester, so it is a mixed Kleisen. What I want you to do now is go ahead and predict the starting materials. So I'll pause right here. Yeah, you have a little think, and then we'll get back to it. I hope you had a little thought, and you can see immediately what we talked about earlier on is that this is the nucleophilic portion of the Kleisen. Why? Because there you can see that the ester with the alpha carbon is still intact. See the ester, so this is the ester here, this whole ester, and including this part of the molecule, is still intact. So the coupling had to be here. So it's a 1 carbon coupling. Did you think about a reactant that you could use? So of course, yeah, here's the nucleophilic center. It's after deprotonation. And then of course we have the attack. So the addition, elimination occurring in this spot. Yeah. We can use other species to form these beta dicarbonyls. Diethyl carbonate is very, very popular because you can see it leads to, yeah, in this case, malanates or different types of malanates. Remind yourself that one of these guys here can be a leaving group. In the case of the chloroformate, this is the chloroformate. You can see, right, we have 2 different types of leaving groups. But of course, the chloride is a much better leaving group than the ethoxide. And so once we attack eliminate, the elimination is going to be the most stable of the most stable base, which is the chloride anion. And so that is the species that will be substituted. You can see quite clearly here where we have the cyclohexanone, that's the inolyzable carbon here. After we attack and eliminate, you can see that elimination occurred of this guy, and of course this is retained. Can you see that? That is retained, and so that's the new coupling right there. Yeah, this is a very, very good compound for synthesis. So we're going to talk about some annihilation, i.e. the formation of wings, yeah? We're going to form some wings. I like these quite, yeah? You can see that if we're going to do annihilation, then one part of the molecule has to be electrophilic and the other part has to be nucleophilic. Of course, we're talking about enolate chemistry, so of course we're talking about generating one part of the molecule, yeah? Generating and enolating one part of the molecule. And then, of course, yeah, we're talking about aldol and Claisen, so one part of the molecule has to be a ketonic or aldehydic. And then in the case of the Claisen, then the other part of the molecule has to be an ester. Let's have a look. So you can see here, for example, in the intramolecular aldol, yeah, we have a dicarbonyl. The dicarbonyl. I can't really deprotonate this carbon because if I deprotonate that carbon to make it nucleophilic, I'll end up with a 3-membered ring. Yeah, that is too strained. So the best I can do with this dicarbonyl is I can deprotonate this carbon and then the coupling will take place. So I end up with a 1, 2, 3, 4, 5-membered ring. You see? Once I deprotonate, I form an enolate. That's a nucleophilic portion of the molecule. And it's going to attack the electrophilic portion of the molecule. We're going to have nucleophilic center attacking the electrophilic center. It's going to be a 5-membered ring, yes? Now, 5 and 6-membered rings are the most likely to form because these are the ones that nature really loves. So if you probe, say, for example, the one that we just looked at, you can see immediately that we have here a 1, 2, 3, 4. So it's a 1,4 diketone. And of course, one of these methyls will act as our enolate, which will attack this guy. So really, we end up with a 5-membered ring. We went via this because once the attack occurred, then of course you can see that literally, yeah, we had a beta hydroxy species as our aldol, well, beta hydroxy is the aldol, and then the condensation takes place. Let's have a look at this question. We want you to pause right here, work on the question, and then we will work with you to solve it. We're going to retro-analyze this compound. And the first thing you got to realize is that this is an alpha beta unsaturated carbonyl. So therefore it came from an aldol. The ring will stay the same. Yeah. Here's our carbonyl. And of course, in the beta position will be our hydroxy. So this is our aldol. The molecule on the left, which is our product, is the condensate of the aldol. The aldol itself came from the dicarbonyl. Because it's an intramolecular aldol, yeah, the dicarbonyl will be, both carbonyls will be in the same compound. So what we got to do is to realize that this is the alpha carbon, that's the beta carbon, and the aldol, in the aldol, of course, the carbonyl that was from our enolate, i.e. our nucleophilic portion, stayed the same. So we can immediately recognize our alpha carbon. That attacked some type of carbonyl. You can see here at the beta carbon, there is no other carbon, yeah, present, so it is aldehydic. So what we're looking for firstly is we're looking for a benzaldehyde type species, i.e. a species where the aldehyde is directly attached to the ring. There is no such thing here. There is no such thing here. Here we have an aldehyde directly attached to the ring. Here we have an aldehyde directly attached to the ring. Then we should count our carbons, because you can see that there's 3 carbons here attached to the ring. 1, 2, 3. That looks nice. 1, 2, 3. That looks nice. However, you can see that the ketonic carbonyl is on carbon 2. Here in carbon 2, there is no ketone. So this one is out. And so we're left with 4 being our only option. Did you get that? Excellent. So we move on. We can talk about this next time we meet as well if you want to. What about this guy? This one is kind of the same idea, but it's much simpler than you think, right? We can do some retro if you want, yeah? You can see that's where some coupling took place. But me personally, right, I looked at it carefully and I want to see if you saw what I saw. So I'm going to pause it right here, and then of course you can have a little thing. So pause your presentation now. What I noticed, yeah, and you should have noticed, is this. I got 1, 2, 3, 4, 5, 6, 7, 8 carbons in my molecule. I kid you not. If you look at, say, E, you got 1, 2, 3, 4, 5, 6, 7 carbons, so that's out. Here, D, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. That's definitely a no-no. Here we got 1, 2, 3, 4, 5, 6, 7 carbons. So that's out. Here we got 1, 2, 3, 4, 5, 6 carbons. That's out. We're fast running out of species, yeah? Here we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Yeah? So yeah, just by a process of elimination, just by counting our carbons, we had a solution. But a lot of people would have realized that we have ketonic residues, right? So we have methyl residues here and here. And so these species here with aldehydic residues would not have worked. And we could work on from there, yeah? That sort of thing. We could even count it from here to here. Say, for example, from here to here. Yeah, 1, 2, 3, 4 membered rings. So that would never have worked. Yeah, so we can eliminate that way as well. We could have easily analyzed it and sort of like went ahead, yeah, and predicted our starting material. So you realize that that condensate was generated from a beta hydroxy species, and of course that should have come from this species here, yeah. You can see the coupling occurred here and here. And if you count the carbons, yeah, if you looked at it closely, then you'd see that you generate C. So there's a number of ways of getting around this, this problem. I hope you got that right. We can move on from here. Here we have an interesting compound. It's called progesterone. So there's a lot of biology here, and it's a gorgeous molecule. Yeah, it's terribly important out there in biochemistries. But we can synthesize this, yeah, in a bucket, and it's quite simple, right? We got 2 steps, right, from this molecule to that one. I wonder what this molecule is called. Yeah, go figure it out. Yeah, but these cholesterol-based species are very important to us. Yeah, I can tell you right now, I haven't asked you a question on about stage 1 or step 1, but you can see immediately there's cleavage. So why don't you tell me what material we use for that cleavage? Yeah, that's organic 1 chemistry. And then of course, now I want you to look at these answers and give us the correct one. So analyze the compound. I'll give you a pause and we get back on the other side. And you should have realized by now, we could use ozone right here, yeah? Could use ozone on the reductive or oxidative condition, don't really matter, because at the end of the day, we have ketones. Yeah? One thing I should show you is this, right? That this is called, yeah? If you notice, right? These ketones, yeah, are in position 1 and 5. This is a 1,5 dicarbonyl. It is also, there's no esters here, so of course it's going to be an intramolecular aldol. So that Kleisen stuff is out, yeah? It's not a michael. So immediately, yeah, we're talking about intramolecular aldol. The interesting thing about these 1,5 dicarbonyls with a hanging methyl is that we can go ahead and form 1, 2, 3, 4, 5, 6 membered ring, yeah? 6 membered ring. So you can imagine we have the aldol, and this is the aldol condensate. It's terribly important to us. And later on, in a couple of slides, well, not today, but in the next block, we will talk about the Robinson ring annulation, and this will be a key step, in fact the final step in the Robinson ring annulation. So to answer your question, therefore, it is of course D. Why? Because aldols do not occur under acidic conditions. Here we got the Diekmann. The Diekmann is kind of simple. Yeah, it occurs with 1,6 and 1,7 diesters. It is, yeah, an intramolecular clison. So one part of our molecule becomes a nucleophilic portion, i.e. our enolate site. And the other part is, of course, electrophilic. You should realize by now, yeah, if it is a clison, yeah, then the enolate, yeah, is retained. So this ester portion of the clison is retained. Yeah, the electrophilic portion, yeah, is what changes. We're going to substitute this guy out, yeah, for that fella. All right, let's have a look at it. So for example, the one we just looked at a while ago is a 1, 2, 3, 4, 5, 6. So it's a 1,6 diester. 1,6 diester. And if you have a 1,6 diester, you can see immediately I can enolize this part of the molecule. Now remember that this part of the molecule therefore will stay the same. And then of course I'm going to attack that part. So that's the nucleophilic portion. This is the nucleophilic portion, and this is the electrophilic portion. And you can see immediately, yeah, the portion that stayed intact, typical of clison, the ester stays the same. And this is, of course, our coupling right there. This is very nice, this reaction, because, yeah, you notice, right, we have a beta ester. And the fun thing about beta esters is you have acidic protons, which we can deprotonate and use for alkylation. So this carbon is nucleophilic, and so we can go ahead and do some alkylation. And then of course it is a beta ester, so we can alkylate, so pontificate, to get a beta acid, which then decarboxylates. So we have beautiful things like this, yes? You can see the electrophilic portion of the alkyl halide. Yeah, so the coupling, the new coupling here of this beta ester is here. And then of course, after I isoponificate, I heat to decarboxylate, and there is my product. It's very pretty. I would like you to go ahead and play with these mechanisms, yeah? It's very important to us. You can see the products of the Diekmann, yeah? The fact is that the 4-membered ring is not viable, i.e. the 1,5 diesters is useless to us. So we're only looking at the 1,6 diesters and the 1,7, which will generate our 6-membered ring. The 1,8 is not very good. So here, for example, we talked about the 1,6. So immediately you can just go ahead and give us the answer. See, that's enolizable. And then of course, carbon 5 being our electrophilic center. It is a symmetrical molecule, yeah, so I could go either way, yeah. And of course, I'll generate a 5-membered ring. Try to give us what that product looks like, yeah. Here, yeah, again, we just looked at this 1,6, yeah, and again, yeah, we know for a fact if you have a 1,6, then 6-membered rings are out. It's going to be 5-membered rings, and of course it is a beta ester, not, yeah, this species that we're looking at. You should realize by now that this bit of acid here is just to quench out the excess base, yeah? Okay. We should recognize these patterns. The patterns are quite simple, yeah? If you have a beta hydroxy, the source was an aldol. If you have a condensate, there's a high probability that is the aldol condensate. However, if you have a beta ester, see the beta ester, then you know immediately this came from a clison. So remember those patterns, yeah, and it will make things quite easy for you. Yeah, you can see that we can easily retrosynthesize this compound. The main thrust behind this retrosynthesis is to remind yourself that the nucleophilic portion of the glycine is an ester, and that ester will stay intact. So here's your ester portion, and so that will stay intact. So this is your new carbon-carbon bond. This is your alpha carbon. That's the beta carbon that belong to the electrophilic portion of your glycine. So identify the alpha beta position which we have, and then use this retro to come up with your compound. So there's the disconnect between the alpha and the beta carbon. And then of course, those are the species that we could work with. Yeah, remember that the electrophilic portion of the glycine is also an ester. Yeah, and so that would what we would put for our forward synthesis. And herein we have a really beautiful question. It says here, in which of the following equation is the main product wrong? We have a halogenation of some sort, which we covered. We can see some sort of alkylation with some hydroxy species on it. We can see, looks like a glycine. And here we have some enamine. We have an enamine being alkylated. That's interesting. Yeah. I want you to probe these reactions, come up with the one that's incorrect. But at the same time, you should realize by now that this enamine chemistry, we will cover them, yeah, in the next section of our lecture, yeah, in the so-called Stork-enamine reaction. It's very beautiful, yeah, and we'll talk about implementing that idea and why we do what we do. So with that, see you in class on Monday, and we'll go over some of these slides, and if you have any questions for us, I'll talk to you then. We'll also review our tests during office hours on Tuesday. Okay, hope you have a great day, or great evening, I should say.